Okay, so stochastic calculus course number 4. Okay. So we have started to work with stochastic processes during the previous session. Okay. I have introduced different notions to compare stochastic processes. Okay. To be equidistributed, to be a version of, to be indistinguishable. We have seen together that when I impose some regularity in the trajectories of the process, to be indistinguishable and to be a version of, okay, it's exactly the same thing. So, I have also introduced the notion of measurability adapted to stochastic processes, okay, just remarking that in fact, even if I can see my stochastic process as a family of random variable indexed by something, I can also see it as a random variable itself depending on two arguments. Okay? So it's what I have defined as to be adapted. Okay? So it's exactly what I have seen, and we are going to remind the definition here. So I have my stochastic process this way. I consider it on R plus, why not? And I have defined to be adapted in the following way. So I consider capital X from, so let's see, TW gives xt of W. Okay, so I am with values in R, equipped with the Borel sigma algebra. And here, okay, I have from R plus d of R plus time omega. Keep in mind that calligraphic A is the sigma algebra on which I define my probability. Okay? So to say that xt is measurable, just means that capital X is considered as a mapping depending on two variables. Okay? And in other words, it can be written this way for all capital T belonging to R plus, for all B belonging to the Borel sigma algebra. I have the following: the set of the TW belonging to 0 capital T time omega such that xt of W belongs to B. But this set, it's the definition of being measurable for the two variables, has to belong to B of 0 capital T time A. So, a priori, so it's something that we are going to handle again today, and a priori this definition so may appear as a little bit theoretical, but we have seen special situations where it's not that complicated to prove that we have something that is measurable. We have seen in particular that if my trajectories are continuous, I am measurable. Okay? And typically, it will be the situation we are going to be interested in for financial applications. So to be measurable is implied by the fact that I have continuous trajectories. So it's not necessary to copy, it's exactly what I have finished with during the previous session. The definition of being measurable for a stochastic process. Okay? So I have this one. And I repeat, if I am continuous, I am measurable. And I have defined at the end of the previous session classically L2 of omega times 0 capital T as the set of the stochastic processes that are measurable with my definition here. And since it's an L2 space, okay, I have an expectation criteria that I have to fulfill with the square here. And here it's the expectation with respect to the product measure, that is the expectation of the integral of the square has to be finite. So it's what I will call L2 of omega times 0 capital T. That is the set of the stochastic processes defined in 0 capital T that are measurable with respect to my definition here, and such that the expectation of the integral of the square is finite, just meaning that I have a product of spaces here. The probability I consider, or the measure I consider here, is the product measure. That is the product of the Lebesgue measure on 0 capital T and the probability I have on omega, that is P. Okay? And of course, the classical scalar product on this space may be derived from this form here. If I have two stochastic processes in this space, what I will denote by x, y, L2 of omega times 0 capital T, will just be, so here you have the quadratic form that may be deduced from this one, okay, that is the expectation of the integral of the product, okay, and the norm is just classically the square root of okay, and I have here usually something that is an Hilbert space, that is a vector space equipped with a scalar product that is complete. Okay? So, when we deal with probability theory, in general, okay, the notion of sigma algebra is related to notion of information. Okay? In general, if you want to do finance, you start from a probability space, omega AP, and you say that the big sigma algebra is the total set of information on the period of interest. Okay? But if you do this, okay, you miss something that is very important, okay, in finance. That is the fact that information evolves a long time. That is that you will have more information tomorrow, okay, than yesterday, and less than today. You have more information today than yesterday, and less than tomorrow. Okay, so you have an evolution of the information across time. Okay, and this is related to a dynamic notion of, let's say, of sigma algebra. That is the notion of filtration. Okay, the filtration that would be simply for us an increasing family of sigma algebra, just in order to model that when I have an evolution of the times, my information increase and increase, okay, with time. Okay. So from a mathematical point of view, we are going to define now the notion of filtration and all the notion of measurability that are related to this notion of being a filtration. Okay? So it's what we are going to do. Do you have some question concerning what I have written here? Okay? So today, the idea will be to start from this definition and to adapt it in the case where here I don't have a single sigma algebra, but a family of sigma algebra that we call the filtration. Okay? And it's what we are going to call the notion of progressively measurability that we are going to study today. Yes?
The last line is...
Which one?
Is, that one is the measure of that.
Yeah.
And that is, isn't that the expectation? I mean,
This one?
No, that.
Yeah. Yeah. So you have this set defined this way, it's a definition, and I just say that the scalar product will be, if you want, the expectation of the product, but the expectation taken on this space, that is a space that is a product space, where I have in fact here my probability P and here the Lebesgue measure on 0 capital T. So the expectation on this space is in fact the expectation of the integral, because I have two variables. Okay? So I have a scalar product defined this way that is related to this quantity, and the norm is just, as usual, the square root of the scalar product. Okay? So you have here a norm in the sense that it fulfills the triangular inequality, it is homogeneous, okay, and so on. It's the classical definition of an L2 space. The only difference is that instead of considering an arbitrary omega, you take for omega this product, omega times 0 capital T. Okay? You change the universe. You have a product set with related sigma algebra that are the product of the sigma algebra, and related probabilities or measure that are the product of the measure or probabilities on each element of the product. Okay? Questions? No? Okay, so let's start with the part concerning filtration. Okay? So first the definition in order to handle it a little, and then we are going to adapt my definition here in the case where, I repeat, I don't have a single sigma algebra here, but I have a family of sigma algebra. It will be what we will call progressive measurability, and that will be exactly the notion that we are going to deal with in order typically to build the Ito integral, for example. Okay, so it's the part 0.5.2. Okay, it's the notion of filtration, and let's say, and related measurability condition. Filtrations and related measurability condition. So as usual, okay, I will have a fixed probability space from the whole chapter. Okay, that will be fixed in the whole chapter. Okay. It's the definition 0.5.x. The filtration ft is just an increasing family of some sigma algebras of calligraphy. Okay, so the EFT are included in calligraphy A, and I have an increasing family. And what is the meaning of being an increasing family? So a sigma algebra is a set of subsets, okay? And I suppose here that Fs is included in Ft if T is greater than S. This is the notion of filtration, increasing family of sigma algebra. Okay? So in general, okay, this notion is used in order to model the fact that you have an information that increases along time. Okay? You have more and more information, and it's typically what happens, okay, in the framework of financial markets. Okay? So I continue in the definition here. So I continue my definition with something that is important to have in mind. Is the following. So a filtration is complete if for all t belonging to R plus, I have n that is included in ft, where in fact n is the set of what we call the negligible sets. The negligible sets are negligible with respect to the probability I have on my universe omega. So be careful, because what I will call as negligible won't be the set of the element of calligraphic A with probability 0, but simply the following. It's the set of the B included in omega such that there exists A belonging to calligraphic A with B included in A and P of A equal to 0. To be negligible, it is not necessary to belong to the sigma algebra. You just have to be included in an element with probability 0. It means that P of B is not necessarily well defined. B is not necessarily in the set of definition of the probability P. It's just a subset of omega, but you are sure that this subset is included in an element of calligraphic A that have a probability equal to 0. Okay? So you are included in someone with probability 0. It's what we call negligible sets. Okay? So I said that if I start from a filtration, it is easy to see that we can always come back to this situation. And you are going to understand in a few seconds why I want to be in this situation, because if I want some natural properties to occur for filtration, it's better to work with complete filtration. Okay, so let me 5 minutes and you will understand what I have in mind. Okay? My question here is just how to pass from a general filtration or to modify it a little in order to obtain something that is complete. So suppose that you start from ft, okay? A priori, you don't know if the negligible sets are inside or not, okay? If you want them inside, you have to add them, okay? So you can add, so you can change ft into what? So you start from your set of subsets. If you want the set of the negligible sets, you add it inside. And the problem is that, in general, if you do this, the new ft, that is ft union calligraphic n, is not necessarily a sigma algebra. When you do the union of two sigma algebra, you don't have in general a sigma algebra. The only general result you have with sigma algebra is the fact that if you take the intersection of sigma algebras, you have a sigma algebra. For the union, no general result concerning this point. But it's not a problem here. What I can do, I want ft inside, I want the negligible sets inside, so I can take the smallest sigma algebra that contains ft and the negligible sets. And in this way, I am sure to pass from an ft that is an arbitrary filtration to this one that fulfills two properties. By construction, the fact that the negligible sets are inside any element of this type here, for sure, by construction, and the fact that I have a filtration, because since ft is increasing, I will have the same for this one. The same for this one, okay? So that's why from now on, we will always suppose that the filtration we are going to work with are complete. Okay, so in this course, can write it this way. In this course, all the filtrations will be complete. We are going to see in a few minutes, okay, why this is important for us, and you will see that it is to have natural results that seems to be intuitive, okay, but that don't hold if I don't suppose completeness of filtration. Okay? An example? Yeah, but in 2 minutes I will give you an example. It's an example that deals with measurability, okay? In fact, if you don't have so suppose that you have a stochastic process, it's just the definition I will introduce in 1 minute, but whatever. You have xt such that for any t, xt is ft measurable. Why not? It's something that we call adapted to the filtration. Okay, I will give the definition in 1 minute. And suppose that you have another stochastic process such that yt is equal to xt with proba 1. The natural result should be if xt is ft measurable, since yt is equal to xt, yt is ft measurable. Something that seems to be reasonable. It's not true if I don't suppose my filtration to be complete. Okay? Other thing, okay, if you have a sequence of random variable, okay, or let's say a sequence of stochastic process, xt, that is convergent, but if you want the limit to have good measurability condition, the limit almost sure, then you have to suppose that the filtration is complete, or the limit won't have the natural property that you will want. Okay? I have the negligible sets inside. Okay? So the definition of being adapted, okay, that I have just talked about. Definition 0.5.9. So it's a notion of measurability adapted to malfiltration, but you will see that in this case it is a very simple notion to understand. Okay, we say that xt is adapted to the filtration ft. So the fact that I am adapted, okay, means in fact that I am adapted to someone. Okay, if I change the filtration, I change the definition. So xt is adapted to ft if for all t belonging to R plus, xt is ft measurable. So in this situation, okay, if I continue the analogy with finance, okay, we are going to enter in more details in a few weeks. If you have in mind the filtration as an increasing flow of information, the fact that I have a process that is adapted means that in order to know the value of xt, that is a quantity that lies at time small t, I need to know the information at time t. It's not possible a priori to anticipate. If I have the information at time t, small t, I can only know the random variables that are defined before. Okay. So it is to be adapted for a stochastic process. And I repeat that a priori, this is a definition. So if I change what is my filtration, I change my definition. Because xt is ft measurable means that the preimage by xt of any Borelian has to belong to ft. If I change ft, I change my definition. Okay? Little remark. If I give you a stochastic process, I said that it is always possible to build a filtration in such a way that xt is adapted to this filtration. So I repeat. If I give you a stochastic process, xt, okay, I said that it is always possible to build a filtration such that xt is ft measurable. And this filtration that it is possible to build from my stochastic process is what we call the filtration generated by the stochastic process. And in general, when we are going to work with stochastic process, filtration we are going to take is exactly this one. For example, for the Brownian motion we are going to study in the next chapter, the filtration we are going to work with will be the filtration related to the Brownian motion and defined this way. So I can write it this way. If we define ft in this way, so I take sigma of xu for u between 0 and t. So I will give it a name. I will call it ft of capital X to make the link with my stochastic process capital X. If we define ft capital X this way, then ftx is the filtration. Why it is a filtration? Because when you increase t, you add more and more random variable inside. Okay. And sigma, this is the notation introduced in the beginning of chapter 0 to define the smallest sigma algebra that make all the xu between 0 and t measurable. The sigma algebra that make the xu between 0 and t measurable, and the smallest algebra that do the job. So if we define ftx this way, then ftx is a filtration such that xt is adapted to ftx. So if I give you a stochastic process defining ftx this way, you obtain a filtration that make the stochastic process adaptive. Okay? And it's what we call ftx, it's what we call, okay, the natural filtration related to a stochastic process x. And I repeat that in this course, in the part dealing with the Brownian motion, or even in the part, the financial one, okay, the filtration that we are going to consider will be in general the filtration generated by stochastic processes, and more precisely, in general, filtration related to the Brownian motion itself, okay, that we are going to define from next week. So to be adapted means that I am adapted with respect to a filtration ft, and that xt is ft measurable. And I said that if I give you a stochastic process defining ftx this way, you are sure to obtain a filtration adapted to, and that make x adapted, okay, this way. And of course, if I continue with my preceding remark, if I want this one to be complete, it is sufficient to take ftx this way to add the negligible sets, and I will obtain this way something that is, okay, the natural filtration related to capital X that is also, okay, complete in the sense of the definition 0.5. Okay? So, to being adapted to a filtration. So now, okay, a little exercise in order to show the interest of being complete for a filtration. Okay? So maybe I will erase this one. it's a little exercise, but that is important in order to. So it's a remark or an exercise. Okay, yes, this one. Remark. I say the following. So if the probability that xt is equal to yt is equal to 1 and xt ft measurable, then yt is ft measurable. So the consequence of this little result we are going to prove is that if I summarize with definition that I have previously introduced, if you have xt that is an adapted process in the sense of definition 0.5.9, and see if I have this for any t, meaning that xt is a version of yt. So if xt is adapted and if yt is a version of xt, then yt is also adapted. Okay? So if you have two stochastic processes, one being the version of the other, then if one is adapted, it will be the same for the other. Okay? So we are going to prove this. So I want to prove that yt is ft measurable. Okay? So I consider a Borelian, and my job is to prove that yt minus 1 of b belongs to ft. It's the meaning of being ft measurable. The preimage by yt of any Borel set, okay, is in ft. And of course I have one hypothesis, or in fact I have two hypotheses. First hypothesis is the fact that xt is measurable, ft measurable, the fact that they are equal p almost surely, equal with proba 1, and the fact that from now on I work with complete filtration. Okay? So how to do? The fact is that they are equal with proba 1. So I know that the set where they are equal is big in the sense of probability. And on this set, okay, x is none other than y. So in fact, I can write the preimage I am interested in, but I can decompose it depending on the fact that I am on this set or not. On the set where they are equal and on the set where they are not equal. Okay? So I can write it this way. I can write it as yt minus 1 of b intersected with xt equals yt, disjoint union, but the other case, yt minus 1 of b intersected with xt different union. Okay? I just decompose this set, okay, on this one, and it's complementary, and I obtain a union that is disjoint, okay? Whatever here, the important is to have a union. Okay? I decompose this set, so it's just, if I do a little picture, I have a set and its complementary set, and I have a set that is here, and I can decompose it as the intersection between this part, for example, union the intersection between the other one. Exactly what I want. Okay. C'est le signe du, excuse-moi. Ça? Union disjointe.
Ah, c'est pas l'indépendance. Ah non,
Dépendance, c'est orthogonal. Non. Union disjointe. Donc je répète, vous avez un chapitre 0 et un début de chapitre 0. Il y a toutes les notations qui sont introduites. J'ai écrit les notes de cours, c'est pour que vous y jetiez un œil. C'est important. Alors après, n'hésitez pas à me demander. En cas de doute, vous demandez. J'ai pas envie que vous passiez la séance avec un doute sur une notation, c'est pas grave. Je vous dis de relire le chapitre, mais je vous rappelle ce que c'est le truc. D'accord, il n'y a pas de problème. Donc ça, c'est union disjointe. Okay? Because the intersection between both of this is empty. Because you have a set and it's complementary set. Okay? Okay, so I have to prove that this one belongs to Ft, and what is my hypothesis? My hypothesis is that xt minus 1 of b belongs to Ft. Okay? Question? No? So I erase maybe this one here. I will keep the definition here because I will need it to prove my result. So if I continue with my equality here, I have yt minus 1 of b, that is equal to what? Here, I know that xt is equal to yt. So the preimage of b by yt is the same thing than the preimage of b by xt, because on this set they are equal. So I can write it as xt minus 1 of b intersected xt equal to yt disjunct union with yt minus 1 of b intersected with xt equal to yt. Okay? And for the moment, from my statement, the only thing I know is that I have the fact that this one belongs to Ft because xt is Ft measurable. So xt minus 1 of b belongs to Ft. But I have to prove that this whole union is in Ft. So there is something that I don't have used for the moment. I don't have used this. In particular, if the probability of this one is 1, it means that the probability of the complementary set is 0. According to my definition here, this one belongs to the negligible sets because it has a probability equal to 0. But if you do the intersection of someone that is negligible with another set, you are sure that this one is negligible because it is smaller than someone that is negligible. Okay? But we have supposed that the negligible sets are inside. So n is included in Ft. So we are sure, so for the moment I work with this one, we are sure that the second part of the union is in Ft. My argument is the following, I repeat. I have the probability of the equality that is 1. So the probability of not being equal is 0. So I am negligible. And if I take the intersection of someone that is negligible with another set, I have something that is smaller, so something that is negligible. Okay? And negligible, from my hypothesis, is in my filtration Ft. So I am in Ft. Okay? Because I am negligible. If I don't suppose this, you can't conclude. It's not possible. Okay? So that's why you need to have the negligible sets inside. Okay? So for the second part of the union, it works. Okay? If I come back to the first here, this one. So I have xt minus 1 of b intersected with xt equal to yt. What I know is that this one belongs to Ft. Okay? What can I say about this one? short, it's exactly what you say. This one is in Ft because it is negligible. So it is in Ft. Ft is a sigma algebra. So it's stable if I take complementary set. Okay, so I can write it this way. This is equal to xt different from yt complementary with this one that belongs to Ft. And so by complementary set and intersection, I am sure to be in Ft because Ft is a sigma algebra. Okay? So I repeat, this one is the complementary set of a set with proba 0. Okay? If I am a set with proba 0, I belong to Ft, so my complementary set also belongs to Ft because Ft is a sigma algebra. So I have something in the sigma algebra here, and also something in Ft. If I take the intersection, of course I am in Ft because I am a sigma algebra. So I have the intersection of two elements in Ft, something that is in Ft. And if I summarize, I have my part in orange here that is in Ft, this part that is in Ft. If I do the union, I am in Ft because Ft is a sigma algebra. Okay? But you see that I have the possibility to conclude. If I can say this, if I don't have the negligible sets inside, okay, you can do exactly the same thing, but can conclude that yt is Ft measurable, while since xt is equal to yt, if xt is Ft measurable, it's not that strange to have that yt is Ft measurable. It's the case if I suppose my filtration to be complete. Okay, that is for any t, Ft contains the negligible sets. Okay. So it was just to underline and to illustrate the fact that I have to work with complete filtration. Okay. If you are okay, we are going to erase everything. And now we are going to extend the notion of measurability, taking into account the fact that I won't have only a sigma algebra calligraphic A, but we are going to work with the filtration, an increasing family of sigma algebra that I suppose to be complete. May I erase the board if you are okay? Yes? So I erase everything. Okay. I just remind the definition of measurability we have seen at the beginning of the session. I have reminded at the beginning of the session. If you have xt t belonging to R plus, I say that it is measurable if and only if for all t belonging to R plus, or all B belonging to the Borel sigma algebra, then the set of the T W belonging to 0 capital T times omega such that xt of W belongs to B. Je ne sais pas ce que vous ferez samedi soir, mais on parlera. This belongs to B of 0 capital T and the notion of measurability I have introduced. Okay? It's exactly what I have reminded at the beginning. Okay? The set of the TW belonging to 0 capital T time omega such that xt of W belongs to B has to belongs to B of 0 capital T time. So it's to make the difference between this one and the notion we are going to see now, that is the notion of progressively measurability. Okay? So it's the definition 0.5.10. Okay. I said that xt is progressively measurable, and from now on I will denote prog measurable this way. Xt is progressively measurable if for all t belongings to R plus, I have the following. TW gives xt of W, where I have here R, B of R, and here I have 0 capital T, B of 0 capital T time omega f capital T. So if for all T belonging to R plus, this mapping is measurable, and if I want to write exactly as previously, it means that, in other words, I have the following for all capital T belongings to R plus, for all B belongings to the Borel sigma algebra, the set of the TW belongings to 0 capital T time omega such that xt of W belongs to B. This set has to belong to B of 0 capital T time f capital T. So you have on the board two definitions of measurability for stochastic processes. This one, the one I have introduced at the end of the previous session, and the new one, to be progressively measurable. Are you able to make the link between one and the other? So just speak over. No? Is one imply the other? What is the difference between the two? So, here I have f capital T, and here I have calligraphic A. And you see that why I call it progressively measurable, because the time here is related to the sigma algebra I have here. Okay, so you have a relation between the time in the interval and the sigma algebra I work with on omega. While in the case of measurability, I have the B sigma algebra calligraphic A for everybody. Okay? So I repeat, if I have f capital T here and calligraphic A here, my question is is measurable imply progressively measurable, or progressively measurable imply measurable? Yeah. Of course, I have, since f capital T is included in calligraphic A, I have an increasing family of sigma, sub-sigma algebra of calligraphic A. I have the fact that progressively measurable imply measurable, for sure. Because if I belong to this one, I belong for sure to this one because f capital T is included in A. So progressively measurable implies measurable. Progressively measurable implies measurable. So in fact, for the moment, I have three notions of, let's say, measurability. This one, the measurability. I have the progressively measurability, but I have also the fact to be adapted to the filtration. That is, for any t, xt is ft measurable. Is there a link between to be adapted and the notion of progressively measurability here? Is there a link between to be adapted and to be progressively measurable? Which one? Say yes.
Yes.
You say what?
Because if I adapted to every single one of it, I use progressively measurable. So being adapted implies progressively. Is that way?
What is to be adapted? Okay, what is to be adapted? If I use my notation here. For all t, xt, ft measurable. This is to be adapted. Okay? And what is this one? That xt minus 1 of b belongs to f capital T. Okay? And what is this one? The set of the w belonging to omega such that x capital T of w belongs to b. Okay? But if you have this mapping that is measurable here, you know that when you have a mapping that is defined on the product of spaces, if you fix one variable and make the other move, you obtain something that is measurable with respect to the corresponding space. So it means that in my definition here, if I fix small t to be a very, very particular element of a Borel set that is just the singleton capital T, so I fix small t to be capital T, but what is remaining will be in f capital T. And if I fix small t to be capital T, here I have xt of w, that will be f capital T measurable, in fact, simply. So I repeat that if I am progressively measurable, okay, I am adapted because of the fact that in the definition here, I can fix one time and take it to be capital T, for example, and then the remaining mapping will be what? F capital T measurable. That is exactly what I want. So I write it here. I have progressively measurable that imply measurable, but you have also progressively measurable that implies adaptive. So it will be the most restrictive one to be progressively measurable because it implies all the others. Okay? And unfortunately, it will be the one we will need, okay, in order to be able to build the stochastic integral and so on. Okay? progressively measurable implies measurable, because f capital T is included in A, and progressively measurable implies adaptive. I continue with my remark here. We have seen together during the previous week that if I start from a stochastic process that is measurable, okay, if I consider f that is continuous and bounded from R into R, we have seen together that as an application of Fubini theorem that xt measurable in the sense of this definition implies that yt defined this way as the partial integral is a stochastic process. It's the family of random variable. Okay, as a consequence of the Fubini theorem. You remind? My question now is what happens if I change measurable into progressively measurable? So if I take for xt something that is not only measurable but a little bit more than this, that is to be progressively measurable. Do you have an idea? I will be a little bit more than a stochastic process, a little bit more, yes, than a stochastic process. So, yt will be adapted to ft. So in other words, if you take the partial integral of something that is progressively measurable, you obtain a stochastic process that is adapted. And something that is that important because, okay, in the chapter 2 we are going to deal with Ito formula. In the Ito formula you have this kind of terms, and these terms will be adapted terms. Okay? And what is the proof of this one? But it's exactly the same as the proof of this one here. I just consider the following. So I consider the following mapping, that is SW that associate to S and W what indicator function of 0t S x S, or excuse me, f of xs of W. So S is in 0 capital T, or in 0 small t, let's say, with B of 0t, and then I have omega equipped with f of small t, and with values in R, B of R. If I am progressively measurable, you see from my definition here that this one, okay, is measurable with here something that is f small t related to the t that you have here. The same definition, here I have written capital T, here I write small t. Okay? So you have this one that is measurable from the definition of being progressively measurable, and by Fubini, so it's measurable and bounded, because f is supposed to be bounded and that my indicator function is bounded. By Fubini theorem, you know that when you have something this way that is measurable and bounded, then the partial expectation or the partial integral here are also random variables that are adapted to by the sigma algebras that I have here or here. So it means here in particular that if I integrate with respect to the first variable. If I integrate with respect to the first, I obtain a random variable that is in fact ft measurable. This is a consequence of Fubini theorem. In the previous session, I have proved this because instead of having ft, I had calligraphic A, saying that if I have calligraphic A, I have something that is A measurable, so I have a random variable, and so I have a stochastic process. Here, I can be a little bit more precise, saying that if I am progressively measurable, here I have no more calligraphic A, but f of small t. And so, this one is not simply a random variable, it is a random variable with respect to ft. And so, I obtain a process that is adapted to my filtration. So when you consider partial integrals, I repeat, of progressively measurable stochastic processes, then you obtain a new stochastic process that is adapted to the filtration. Okay? So come back to the argument I have given to you for this one. The only thing that is changing is that instead of having calligraphic A here, I can put f small t by the definition of being progressively measurable. Okay? And so this one becomes not only a stochastic process, but a stochastic process that is adapted to my filtration. Okay? So once again, when I see this definition, it is a little bit theoretical. Okay? So we say that in practice, if I have to check that someone is progressively measurable, if I have to come back to this definition, it may be a little bit complicated. Okay? So what we are going to see now in 2 steps is that in fact you have a lot of stochastic processes that are measurable, that are progressively measurable. We have seen together that you have a lot of stochastic processes that are measurable, the one that have continuous trajectories. If I am continuous, I am measurable. And then just if you add a little something to be continuous, you will be progressively measurable. That is, if you are continuous and adapted, you are progressively measurable. If you are continuous and adapted, we are going to prove that you are progressively measurable. Okay? So something that is comfortable to prove because by continuous classical analysis, okay, and the fact that I am adapted just means that for fixed t, I have to prove that I am ft measurable. Something that is a priori a little bit less complex than to prove this one. Okay? So continuity implies measurability. Continuity plus being adapted will imply progressively measurability. But before to do this, okay, just let me show you an example of something that is progressively measurable. A basic canonical case of something that is progressively measurable, because we are going to use this canonical form in order to prove that continuous plus adapted implies progressively measurable. So I keep the definition on the board, and maybe what I can do is just to change this one this way. So you have the definition of measurability this way, and you have the definition of progressive measurability this way. Okay, F capital T. So in this way you have both definition on the board. Okay? So you have here the definition of measurability and prog-measurability. If you remove the part in red, you obtain the definition of measurability, and if you add the one in red, you obtain the progressive measurability. Do you have some questions? No? So I erase if you have no questions. So I repeat, I know that it is a little bit technical, it's not, and it won't be the case the whole course. Okay? In particular, if you don't have spent time in the previous session, okay, so it should be a little bit strange. But I will need this notion. I will need this notion concretely. I will need this notion in order to build a stochastic integral that will be defined on particular sets of stochastic processes that are progressively measurable. Okay, so it's not just to do only theory, okay, it's because I need to have a tool for the financial chapters, a tool that will be defined on this kind of processes. But you will see that in practice, okay, once everything will be built, progressively measurable for you will be something that is continuous and adaptive, more or less. Okay? Something, I repeat, that is easier to handle than this definition, but in my construction of the stochastic integral, because I will build the stochastic integral, I will need these spaces, okay, to work with. So I repeat, may I erase? Yes? I erase. So it's an example, and in fact, with inside a definition of a set that would be important. It will be the set of the elementary stochastic processes that are progressively measurable. You see. I consider the following. I consider T1 strictly less than T2, less than Tn. I suppose Tn to be equal to capital T, and T1 or yes, equal or. Positive. I can do it this way. I will do it this way. T1. Let's do it this way. So I have T0, T1, Tn, avec the first one that is equal to 0, the last one that is equal to capital T. Okay, so if you want, you have 0 capital T, and you consider a subdivision. Okay? You have a subdivision of 0 capital T made with n plus 1 points. Okay? Okay. So I define xt in the following way. So xt to be equal to the sum, let's say from I equal to 0 to n minus 1 of f ti, indicator function ti plus 1 t, where fti is fti measurable. So why not? So I have a very particular stochastic process that is in fact with trajectories that are piecewise constant. Okay? Trajectories that are constant on these little subintervals here. Okay? So I am equal to ft0 on 0 t1, I am equal to ft1. So if I want to do a picture of this one, okay? So between 0 and t1, this way, you are equal to f0. Okay. On T1 and T2, for example, this one, you are equal to T1. and so on. Okay? And keep in mind that here I have random variables. So it means that my constant will move depending on W. Okay, so I have a stochastic process here. If you are in this definition, you have a W that is idle. It's xt of W that is equal to fti of W. So you have a stochastic process. And it means that the trajectories look like this one, okay, with my constant that will change depending on the choice of W. Okay? So you can see this as the analogous of stepwise function. The stepwise function, if you remind that you have used in order to build the Riemann integral. Stepwise function in order to build the Riemann integral with the area of the rectangles and so on. Okay? And here we are going to call elementary stochastic processes, okay, elements of this form that are just stochastic processes with trajectories that are piecewise constant. Okay? And you will see that it is on this kind of processes that we are going to define the stochastic integral. First. Okay, so I have this one, xt, that is defined this way, okay, where fti is fti measurable. I said the following. I said that xt is progressively measurable. Xt is progressively measurable. Okay, so these kind of processes are progressively measurable, and what is important to have in mind is this one, that the Ti here is the same as this one. It means that the measurability condition on this random variable is related to the left part of my interval, the beginning of my interval. If you change this, okay, you won't be progressively measurable anymore. If you put here this one to be fti plus 1 measurable, you are not progressively measurable. Okay, but I have to prove this. I have to prove this here. So I just have to be careful, okay, because here I have the capital T that is in the definition of this one, and I have the capital T that is the arbitrary capital T in this definition here, okay? So, what can I do at this time, okay? I keep this one this way because after I will introduce notation, but here, okay, I will give another name to the capital T here, the arbitrary capital T. So I consider let T0 belonging to R plus. And I want to prove that I am progressively measurable, so that is, I am interested in this set. And I want to prove that it belongs to B of 0 capital T time, or to B 0 T0 time F T0. Okay? So my job is to prove that the set of the TW belonging to 0 T0 time omega such that xt of W belongs to B. I want to prove that this one belongs to B of 0 T0 time F capital T0. And of course, in my very particular situation, I will be able to express this one in a very precise way because I know what is the form of my stochastic process. This stochastic process is not nothing, okay? I just have to be careful because in fact I have two situations. Because I have my 0 capital T here and I have my T0. That is the one coming from the definitions here. So I will have two situations. The one where T0 here, that is before t, or the one where t0 is here. Okay? So I will do one of them. Which one do you want? The same. Okay, so I said that in order to write this properly, I have two situations. The case where my t0 is here, and the case where my t0 is after or before capital T. Okay? So which one do you want? The first? So this one. Okay.
Why is it T0 and not T?
No, it's just because I have written capital T here. So, okay, so I consider an interval, I consider a subdivision, okay, and I define my process this way. It is defined on the interval 0 capital T. Okay, but in fact my process xt is just a process, if you want, on R plus. The only thing is that for T that is strictly greater than capital T, I am 0. Okay, I have something that is just defined with non-zero value on 0 capital T. In my definition here, I have to prove that this one belongs to this set for any time in R plus. It's to avoid confusion between the time involved in the definition of X and the time that is an arbitrary time in the definition. Okay? So if you want here, I can put 0, 0, which is nothing. Okay? Or this one here. So the first case, tell me, okay? So if I am in the first case, since I have a subdivision, I can give a name to the two consecutive points on which, okay, where t0 belongs to the interval. Okay, so I can call it, I don't know, I can call it, but here, t I0, and here t I0 plus 1. Just to say that I have an element in 0 capital T, it belongs to at least one of the little interval of my subdivision. Okay? T I0 plus 1, just to say that T0 belongs to this interval. Okay? I have this 0 capital T. I have T0 that is inside. Since I have a subdivision here, I am sure to have two consecutive points. Okay, such that here and here I have T I0 plus 1 here. Okay? So what is this? I see that my values depend on where I am. Okay? So I can write it this way. I can write it as 0 T1 times what? So on 0 T1, I am equal to ft0. So on 0 T1, here my xt of w or my xt is just ft0. So I will have here time ft0 minus 1 of b. 0 T1 times ft0 minus 1 of b. This is this one for t belonging to 0 T1. Union of what? Until the last. What is the last? Here is I am between t I0 and t0. So union t I0 time t0 time here on this set I am equal to f t I0 minus 1. So I have this. I just write the pre-image taking into account the fact that depending on which I am in the subdivision, So you have the elements of the subdivision here. If I am here, I am equal to ft0. If I am here, I am equal to ft1. If I am here, I am equal to fti0. Okay? I have this one, and now I just have to have a look on what happened concerning the measurability of each set here. I know that ft0 is fti measurable. So you have something here that belongs to calligraphic ft0. You have here something that belongs to calligraphic fti0. But I know that capital T0, okay, is greater than all the times involved in my union here. So I have this one that is included in F capital T0, this one that is also included in F capital T0, and so I have proved exactly what I want, that writing this pre-image here as this union, I prove that I belong to the Borel sigma algebra of 0 T0 time F T0. And so a process that can be written this way is in fact progressively measurable. Okay? It's an argument I have already used with you, this one. When I have proved that, that if I am continuous, I am measurable. I am approximating my continuous process by something that is stepwise constant, and then express this pre-image this way. Here, the only thing that I use that is a little bit more is that I know that the FTI are FTI measurable. Okay? So the stochastic processes that are piecewise constant, with trajectories that are piecewise constant, and such that the measurability of my constant here, my random constant if you want, the measurability of this one is related with the left time of my interval. That is FTI is FTI measurable. The FTI coming from this one here is something that is progressively measurable. And I repeat that if you change the condition here by something that is a little bit more than TI here, you don't have this property anymore. You don't have this property anymore. It's because if you want, the measurability condition here is never in advance with respect to the time I have in my in my interval here. Okay, my interval TI plus 1. Okay? Do you have some question before the break? No? It's okay? Break? Let's say 10 minutes. Okay, so I just introduced a notation concerning the set of elementary stochastic processes here. So I denote by epsilon the set of the stochastic processes of this form here, imposing that this one is not only FTI measurable but also in L2. Okay? In L2. And in this case, I know that epsilon of 0 capital T times omega will be included in, so just this way, is included in L2 of 0 capital T times omega. Because I have indicator functions that are bounded and I have the FTI that are in L2. Okay, so if I consider the stochastic process defined this way, it belongs to L2 of omega of 0 capital T times omega. I have proved that it is progressively measurable, so it is measurable. Okay. And in this situation here, if I want to compute the expectation of the integral of the square here, what I obtain in this situation. So by Fubini theorem, I can do the expectation first or the integral first. It changes nothing. Okay. So here you have something that depends on t, something depending on w. So it's the product of one part depending on t, one part depending on w. And I have, in this case, the sum from I equal to 0 to n minus 1, f the expectation of f ti square multiplied by ti plus 1 minus 0. Okay? Because the integral of the indicator function is just the length of the interval. Okay? And you know that when you do the product of indicator functions that are disjoint, okay, the product of the indicator function is empty, is a 0 in this situation. So I obtain exactly this value for the expectation of the integral of the square. That means that, in other words, the norm of x in L2 of omega times 0 capital T here is just the square root of what I have written here, the sum from I equal to 0 n minus 1 expectation of fti square ti plus 1 minus ti. And you will see that this set will be very important for us. The set of the elementary stochastic processes, okay, defined this way. You know that long time ago, when you have built the Riemann integral, you have built using mappings that are stepwise constant, function escalier. And then you extend this definition to more complex mappings, okay, to have the Riemann integral you know with all its properties. For the stochastic integral, we are going to define in the chapter 2, after the definition of the ground motion in chapter 1. But we are going to use this kind of stochastic process in order to define the stochastic integral, first for this process, and then to try to extend this stochastic integral to more general processes. And you will see that the set of the stochastic processes on which I will be able to define the stochastic processes will be the ones that are in this space and that are progressively measurable. Okay? It will be to define the stochastic integral, that is the integral with respect to the Brownian motion on this set of stochastic processes. So I have introduced this notation here. Yes. So, square integrable, no problem, meaning that the expectation of the square is finite. When I put FTI inside, it means that I am measurable, but with respect to this sigma algebra here. Okay? So you are measurable with respect to FTI, like my definition here, and I add just that the expectation of the square is finite also. Okay? So I have this one. Right, to conclude this part, two little things, and after we are going to pass to the part concerning martingales that is a little bit less technique, okay, with computation that are more classical to do. So first a little proposition, a definition, and a theorem. And I won't do the proof of the theorem, maybe in exercise, but not today because it is a little bit technical and it will be sufficient for technical things. So, if I come back to the definition of being progressively measurable, I am agree with you that it is a little bit technical, for sure. But there are some special cases where it is possible to prove that I am progressively measurable, and to prove this one, okay, without using the theoretical definition. What we are going to see here, that is in fact a consequence of what I have done for this kind of process, is the fact that if you are continuous and adapted, you are progressively measurable. So it's the proposition 0.5 point, I don't know what, 0.5.9.1. Proposition 0.5.1. If xt, is continuous, meaning that its trajectories are continuous, okay? On the set of probability 1, so xt is continuous and adapted. Then xt is progressively measurable. So in particular, if you have a process that is continuous, since I have said today that you are always adapted to what I have called the natural filtration, you will be progressively measurable with respect to your natural filtration. Okay? So in most of situations, to prove progressively measurability, you will have to prove only the fact that you are continuous, something that is not that theoretical to prove. Okay? In fact, I have already done the proof of this. If you come back what we have done during the previous week, I have proved that continuous implies measurable. We have proved this together. Now I just have to have adapted to prove that I am progressively measurable. So quickly the idea, because all the technical points were proved during the previous session. So if you remind, in order to prove that continuous implies measurable, I have done this in 2 steps. I have first approximated my process by a stochastic process that is stepwise constant, proving that when I pass to the limit, I obtain my process, and then proving that the stepwise process was measurable. Here it's exactly the same idea with exactly the same approximation, so I just remind you what I have done. So I have 0 capital T and I have my process that is continuous. Okay? So what can I do? I can consider a subdivision here. Okay? So for example, T over N, and here you have N minus 1 T over N. And the way to approximate is to say the following. On this first little interval, I will approximate my process by this value here, that is in fact x0. Then on the next little interval, I will do this, approximating by x t over n, and so on. And one approximation I can build this way. It's x n t and w defined as a sum of indicator function of this type here, t I over n, t I plus 1 over n. And on the interval ti over n, ti plus 1 over n, I approximate my process by x ti over n. And I do the sum from I equal to 0 to n plus 1, no, to n minus 1. So I remind you, so it's something we have already seen together during the previous session. Together during the previous session, we have proved that xn converges toward x, okay, on 0 capital T. I have the convergence, it's a real approximation, okay? When n goes to plus infinity, that is when the step size of my subdivision goes to 0, okay? But what I have done just previously, what is the xnt I have defined here? I have a sum of indicator function, and if I suppose that my process is adapted, if I suppose that my process is adapted here, I have something that is fti over n measurable. So not necessarily in L2, but fti over n measurable, and we have proved just before the break that this kind of process is progressively measurable. It's exactly the job I have done just before the break. Okay, I have xn that is progressively measurable because it is a stochastic process with piecewise constant trajectories, and with the fact that the measurability condition on this one is related to the smallest time in my interval. Okay, so I am not necessarily in epsilon because I don't know if this one is square integrable or not, but okay, I have for sure something that is progressively measurable as proved, okay, with the sum of the fti indicator function of ti plus 1 is exactly of the same form. Okay. Convergence, because I have done the job during the previous session and disused the continuity of the trajectory. Okay, previous session, that's right here. Previous session. And this one, just before break. If I combine both of them, the limit would be progressively measurable because measurability is preserved by passing to the limit. Okay. So to prove that continuity implied measurability, I have used this approximation. If I had to be adapted using the same kind of approximation, I prove that I am progressively measurable. Okay? And so what is it is important to have in mind for you is that, in general, okay, to prove that something is progressively measurable, you will have simply to check that the trajectories are continuous with power 1, okay? And that this process is adaptive, and typically if you work with the filtration associated with the stochastic process, continuity will be sufficient to prove. Okay? So continuous plus adapted implies progressively measurable. So now a little definition, very basic, a theorem, not basic but that I will admit for the moment. I will see if I have the time to do. Maybe in the tutorial, I will see. But you have the proof on the lectures notes. So we are going to define the set of the stochastic processes that are progressively measurable and square integrable. And the powerful result that we have is that what I have called the elementary stochastic processes are dense in this set. Meaning that if I have a stochastic process that is progressively measurable and square integrable, then it can be seen as the limit of a sequence of elementary stochastic processes. Okay? So it's what we are going to write if you don't have questions. So are you okay? So I don't enter into too much details because it's exactly what we have done together during the previous session. If I remove this part here without putting adapted, I have proved that if I am continuous, I am measurable. If I add the fact that I am adapted, I can say that here I have something that is FTI measurable, And just before the break, we have proved that these kind of processes that are piecewise constant, with my constant here that is measurable with respect to this time, I have something that is progressively measurable, and so I have something that is stable by passing to the limit, as all the measurability notions. Question? No? Encore? Measurability always passes to the limit. Keep in mind that when I define measurability, it's what? I consider a stochastic process as a mapping depending on two variables. I have sigma algebras on this, so it's a measurability, in fact, adapted to a particular case. In the case of progressively measurability, it's exactly the same. I have two variables. The only thing that I change is that I replace my calligraphic A by F capital T. So it's a notion of measurability that passes to the limit also, without problem. All the measurability notions pass to the limit. So here, so I can prove it so. My set being compact here, I can prove that I have this, I have that, so this way. The maximum on 0 capital T of xnt minus xt, okay? Convert this towards 0, almost surely. Okay? And I can take the max because, okay, I am continuous on a compact set, so the convergence is uniform, in fact, in the time, as we have proved during the previous session. So this one means this one. Okay? Other questions? D'autres questions? No? So I will introduce a definition that in fact is not that new, but I introduce it because I will need it after, and just state a result that I will use extensively in chapter 2. That is the basis of the construction of the Ito integral. So may I erase the board? Yes. So let's do. So keep in mind that I have defined previously, L2 of omega times 0 capital T I have defined L2 of omega times 0 capital T as the set of the processes that are measurable, and such that the expectation of the integral of the square is finite. But now what I do exactly the same, but with progressively measurable instead of measurable. L2 prog of omega times 0 capital T is the set of the stochastic processes that are progressively measurable, and such that the expectation of the integral of the square is finite. Of course, since I know that when I am progressively measurable, I am measurable, I have L2 prog that is included in L2. And according to my previous definition on the set of the elementary stochastic processes that are square integrable, I can say that epsilon is included in L2 prog that is included in L2. Okay? And the theorem that I will just state now will tell me the following. Question? 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 Pas posé de question. Tu vas me demander à moi? Non? Okay, so it will conclude the section. So in fact, it's a result that is not that surprising, okay? Because if you come back to the case of the Riemann integral, it is an old case you have seen. The set of the piecewise constant mapping, in fact, are dense in the set of the Riemann integrable function, and here it will be more or less the same with my elementary stochastic processes and L2 prog. So it is the following thing. Okay, so L2 prog omega times 0 capital T is complete. So I have an Hilbert space, in fact, is complete, and epsilon of omega is dense inside. Okay, you have the density of the element in epsilon among the element in L2 prog. And the way we are going to use this kind of result later on is that if I have an element in L2 prog, it is possible to find a sequence of elementary stochastic processes that converge. And I remind you that the norm in this situation, okay, is exactly the same as the norm in L2. So this one equal to the expectation of the integral of this square. Okay. So you have the proof of this result in the lecture's note. So it's a classical way to approximate, okay, mappings. And maybe I will do the proof, okay, later on in an exercise tutorial section. Okay. So it closes the technical part concerning measurability, filtrations, and so on. Okay. So now we are going to come back to things that are a little bit less complicated from a theoretical point of view. So what we are going to do now, okay, is to remind the definition of what are martingales in continuous time. And typically, okay, I will remind 2 or 3 results that I will use in the remaining of the course. Okay, so it's not a course concerning the whole theory of continuous martingales, okay, but just I will emphasize all the points that we need in the following. Okay? So it's the part. This one, or maybe no. Sorry, it's not what I have to do. I have a little part before. It is the notion of Gaussian processes, in fact, before to speak about martingales. So it's not that complicated. So just copy this, tell me that when it is okay. It's okay, so the definition of L2 prog, it's the same than L2, I just add progressively measurability instead of measurability, okay? And this result, that is really powerful, huh? You have the proof in the lecture's note that this one is in fact an Hilbert space, and this one is dense in L2 prog. For any element in L2 prog, it is possible to find a sequence of elements in this set that converges in the sense of this law. We have the density of epsilon in L2. and I repeat the last time that when we are going to build the stochastic integral, the way we are going to do is to build it easily on epsilon, and then using the density argument, we are going to be able to extend it to all the elements of L2 prog. This is the idea and the way we are going to use this result later on. Okay? So I erase. So just a little chapter concerning Gaussian processes, okay, and I think that I will finish by this one today. Be enough. Okay, so I need maybe 20 or 25 minutes, okay, so it won't be 7, it won't be half, okay, because I have to check if I have my meeting or not, okay, but I will do. So Gaussian processes, few things, just basic definition and example, in fact, because we are going to spend all the chapter 1 studying probably the most famous Gaussian process, that is the Brownian motion. Okay? So Gaussian processes. So in the first session, we have spent time on Gaussian vectors. Okay, so I remind you that if I have a single random variable, my x is Gaussian, I have a lot of possibilities to define a Gaussian random variable. I have the characteristic function. For example, okay, I can define it this way, I can define it by its density function. Okay? So you have to know the characteristic function of a Gaussian. Okay, it is this one. I have introduced the notion of Gaussian vector. What is a Gaussian vector? The question? How to define a Gaussian vector? So all the vectors, which vector? Not understand. So it's the component, it's not sufficient to have a Gaussian vector. So if I have a Gaussian vector, my coordinates are Gaussian, but it's not the definition. No. If you are independent and my coordinates are Gaussian, I am a Gaussian vector, but it's not the only way to be a Gaussian vector. What is the general definition? Oh, oui, la finition. Linéaire, ça suffit. C'est pareil. Okay. Any linear combination of the component is a Gaussian random variable in the sense of the previous step. I can write it this way. For all x belonging to R to the power n, if I denote this vector by capital X here, the scalar product between x and capital X is Gaussian in the sense of the previous definition. Okay? So any linear combination of the components is a Gaussian, real Gaussian random variable. It's the way I have defined to be a Gaussian vector. Okay? So, in the case of a real Gaussian random variable, we know that you can characterize it by its mean and its variance. The mean here, and the variance that completely characterize the family of being Gaussian. Okay, it depends on two parameters. In the case of a Gaussian vector, it's more or less the same, in the sense that I have a formula for the characteristic function of the Gaussian vector. We have proved this together. And in fact, this characteristic function depends on two things. the vector of the mean. Okay. The mean vector. And what?
Variance matrix.
The variance covariance matrix. So I can characterize my Gaussian vector by the mean vector and the variance covariance matrix. So two parameters, one that is a vector and the other one that is a matrix. But the notion of Gaussian process will be by the next step to pass from 1 to a finite number to a Gaussian process. So it's the definition here. You will see in this definition I use the previous step. In the definition of Gaussian vector we are going to use the previous step that will be this one, the notion of Gaussian vector. Okay? So definition 0.5.12 xt t belonging to R plus is a Gaussian vector, a Gaussian process, excuse me, if, in fact, if all the Gaussian vectors that can be built from this stochastic process are Gaussian vectors. In other words, if for all n belongings to n star, for all t1, tn belongings to r to the power n, xt1, xtn is a Gaussian vector. So xt is a Gaussian process if for all n belongings to n star, for all t1, tn belongings to r to the power r plus, in fact here, r plus to the power n, xt1, xtn is a Gaussian vector. So it means that you have something indexed by r plus, and in order to be Gaussian, it means that all the related vectors you can build are Gaussian vectors. Okay? Here? This one just means that I choose an arbitrary number of instants in R plus, and all the related vectors are Gaussian. This is the meaning of being the Gaussian process. Okay? So if I want to characterize the distribution of this Gaussian process, it means that I have to be able to characterize the distribution of all the related Gaussian vectors. And I know that this Gaussian vector is characterized by what? By its mean function, by its mean vector, and by the variance covariance matrix. Okay? And in fact, my Gaussian process will be characterized by two parameters, in fact, that are two mappings. What we call the mean function. The mean function, that is what? That is small m from r plus into r, that associate to any t the expectation of xt. If I give you explicitly small m, then you will be able to find explicitly what is the expectation of this vector here. It will be mt1, mt2, mtn. Okay? So in order to characterize all the Gaussian vectors, I have to know what I call the mean function, the function that gives you the mean of the Gaussian vector. And you have another thing, that is the variance covariance mapping function. So what I have to know? I have to know all this matrix here. Okay, but if I need to know all this matrix, I just have to know what are these terms. In fact, so the mapping, the variance covariance function that is called gamma, is a mapping from r plus square into R that associate to any T and S the covariance between xt and xs. So if I give you m and gamma, you will be able to find the expectation of all these vectors and all these variance covariance matrix. That is, you will be able to know all the distribution of these vectors here, and so to know the distribution of the Gaussian processes. So just a remark, so for the mean function I have no conditions. I have no conditions in the sense that the mean vector here can be anything you want. You have no condition on positivity, something like this and so on. Okay? For gamma it's a little bit different because here first I see that gamma is symmetric. Because gamma of xt, covariance between xt and xs is the same than the covariance between xs and xt. So gamma fulfills two properties. Gamma of st is equal to gamma of ts. So my gamma can't be arbitrary. It has to fulfill this condition by the fact that the covariance is symmetric. Okay? So it's the first thing. Second thing, gamma allow me to recover all this matrix here. Okay? But what is the variance covariance matrix? It has some properties. It is symmetric from this fact, and also positive. We have a positive matrix. And so you have a variance covariance matrix that is a matrix that is positive in the sense of the symmetric matrix. Okay? And it means that it fulfills this one, and it fulfills the fact that for all n belonging to n star, for all T1, Tn belonging to R plus to the power n, if I build a matrix this way, gamma Ti, Tj, this matrix has to be positive in the sense of the matrix. Okay? You have a positive matrix because this is necessarily the variance covariance matrix related to my vector xt1, xtn. So I repeat, I said that Gaussian process defined this way from the fact that all the vectors you can build are Gaussian vectors in the sense of this definition. If I want to characterize the distribution of a Gaussian vector, I need the mean, the expectation, the vector of expectation, and the variance covariance matrix. If I want so to define the distribution of the Gaussian process, I need to know the distribution of all these vectors. To know the distribution of all these vectors, I know to know all their means. This is possible if you know this one. And all their variance covariance matrices, okay? That is possible if you define gamma this way. If I give you gamma and m, you are able to build all these two for any xt1, xt2, xtn. My second remark is that for m, I have no conditions. My mean can be what I want for Gaussian random variable. This is not true for gamma, because for gamma, gamma is implied in the construction of variance covariance matrix. These matrices are symmetric. That's why I need to have gamma of st is equal to gamma of ts. And what is more, since gamma ti tj is in fact the covariance of xti xtj here, it's a matrix that is positive in the sense of the matrix. Okay? So it needs to fulfill these two. Okay? So for m, I can give you what you want, the exponential, the logarithm, if I have not 0 here, what you want. Okay? For this one, it's a mapping depending on two variables, but that need to fulfill some properties. And in order to conclude today, we are going to see an example of such a mapping. A mapping such that, well, that is symmetric, not that complicated, but such that for all T1, Tn, the related matrix is positive. Okay? So it's what we are going to do here, and I will conclude by this today. So let's see an example. So example of such a gamma. I define gamma this way here. From R plus square into R, let's say, that associates to T and S the minimum between T and S. Why not? Okay? My job is to prove that 1 and 2 are fulfilled. So this one fulfills point 1 and point 2 defined this way here. For the point 1, it's not that complicated. Huh? The minimum between S and T is equal to the minimum between T and S. Okay? What I have to prove in fact is more this one. Okay? So I take an arbitrary n, I take T1, Tn, and I want to prove that I am interested in this kind of matrix. The minimum between Ti and Tj, for I and j between 1 and n. And what is interesting is that I have to prove that I have a positive matrix, whatever are T1, T2, Tn. Okay? Independently of the choice of T1, T2, Tn. Do you remind how to prove that the matrix is positive? Yes, you can use the determinant here. You can try, but it will be complicated if you do it this way, but it's possible. Okay? But with this matrix here, possible. Not that easy. So the determinant is in fact, the condition with the determinant is in fact an equivalent, okay, characterization of being positive for a matrix. Do you remind? By the basic definition in fact.
Indeed, a quadratic form.
Yeah. So you have a symmetric matrix. You can define the quadratic form related to this symmetric matrix, and we want this quadratic form to be positive. In other words, I remind you that Aij is positive if and only if for all x belonging to R to the power n. If I consider the double sum, the double sum has to be positive. This is the definition of being positive for a matrix. Okay, here you have in fact, if I call this matrix A, you have A times X transpose here. And we want here that the quadratic form related to this matrix to be positive. So it is what I have to do for this one. Taking for Aij the minimum between Ti and Tj. Be careful, because you have to prove this one independently of the sign of x, the component of x. Xi and xj, you have no idea concerning the sign of this point. It's for all x in r to the power n, that is for all xi and xj. Okay. So if I take my example here, what I am interested in, I am interested in this quantity, but with aij that is given by the minimum between ti and tj. Okay? And I want you to prove that it is always positive. Always positive. So I know that here I have instance so that I have positive numbers, so the minimum is positive, but here xi and xj are a priori completely arbitrary. Okay, and I want to prove that this double Q is always positive. So there are several ways to prove this result. You can do it by induction, for example. Okay, induction on the number of points here, the T1, Tn. Okay, it's one possibility to do. So if you do it by induction, I can use your idea of determinant and you develop by, with respect to a line or a column, the determinant. It's possible to do like this. More interesting is the following trick. So something that is not that complicated, but when you see it, it's okay. The minimum between 2 points. I said that the minimum between, so you have a formula for this one, you have the minimum between A and B, that is what? The middle of the interval plus 1/2 the length of the interval. It's one way to define the minimum, excuse me. If I want to define the minimum between 2 points, okay, I take what? The minimum is equal to what? The middle minus 1/2 the length of the interval. The maximum will be the middle plus 1/2 the length. It's one possibility. In general, it's a formula we use in order to prove that the minimum mapping is continuous, because it is made with a middle, average and absolute value, let's say. It's not the one we are going to use now, but the one we are going to use is this one here. The integral between 0 and capital T, or in fact 0 plus infinity, are you okay with this? What is the indicator function, or what is the product of two indicator functions? If you have a set A and a set B, what is the product of the indicator function? Indicator function of the intersection. So this product is the indicator function of the intersection. But what will be the intersection of these two intervals? Exactly the interval 0, the minimum between Ti and Tj. Here you have indicator function 0, minimum between Ti and Tj. And when I take the integral of the indicator function, I recover exactly the length of the interval, that is here, the minimum between Ti and Tj. The idea here is to write the minimum between 2 points using indicator functions. And why I do this? Because when I have this expression, okay, it's not possible to separate Ti from one part and Tj from the other part. But here, it's exactly what I do. Because I express it as the integral of the product of indicator function, and you see that I have a product here, where this one only depends on Ti, and this one only depends on Tj. It would be perfect to do what I want. In fact, perfect to do what I want. So what I want to do, I am interested in this one, and I want to prove that it is always positive. I replace by my little trick here. This one. What can I do now? But I have one part depending on I, the other part depending on j. In fact, I can write it this way. So, using the linearity of the integral, I put it outside. And I have, in fact, I can write it this way, the sum from I, xi, indicator function is, the other term being exactly the same. Something like this. So excuse me, it's not a capital T, it's a plus infinity here. You agree with what I have written? So I use the linearity, so I can put the integral before. Then I have a double sum, but in fact I have a part in I and a part in j. I can separate the double sum. Each term being equal, I obtain the square of this sum here. Simply. And so, without assuming anything about the sign of the xi, I prove that this double sum is always positive, because it's the integral of a square, okay? And so I have proved that all these matrices are positive in the sense of the symmetric matrix. Is it clear, this one?
No.
So, so I can use the linearity of the integral. You are okay with this? So I can write it this way. It's the integral between 0 and plus infinity. Sum of I, j, xi, xj, indicator function PIS, indicator function 0, PAS. You agree? So the fact is that here I have a double sum. I have this term here. Okay, so you know that here I have two finite double sums. I can do the sum in the order I want. Okay, it's a kind of Fubini theorem, but in a very, very restrictive framework. Okay, the case where I have finite double sums. So if you want, this one can be written like this. First, I do the sum with respect to I, and then the sum with respect to j. But if I first do the sum with respect to j, I can remove all the terms that depend on I. Okay? And now I have something that doesn't depend on I, and so this is just the product of this term. Okay?
But why are they the same?
Yeah.
Ti and Tj.
Because you do the sum. I don't say that Ti and Tj are the same. I just say that this sum is the sum over all the terms of the xi. So you can change the name of the index if you want. I just do the sum over all the component of my vector x, r, and the indicator function. If I remove this one, I obtain exactly the same sum here. So that's why I have the square. Okay? So I obtain the integral of something that is positive. The integral of something that is positive, and at the end I have exactly what I want. That is, this sum, this double sum is always positive. Whatever being the Ti-Tj and the Xi-Xj. As you will see in the chapter 1, the Brownian motion is the unique Gaussian stochastic process with a mean function equal to 0 and a variance-covariance function that is equal to this one. It's one way to define the Brownian motion. Okay? Do you have questions? So see you next week.